The 401, CISP 401, that's Java.
Object-oriented Java.
Mm-hmm. Yep, that's CISP
Yep, working.
401. Well, I mean, Java is not actually very difficult to learn. It is
No.
kind of more of a, just having to most most of the time it has to do with people have not been keeping up with the class. So at the end of the semester, that gap becomes really really big,
Yeah.
and becomes to many people becomes something that they cannot easily recover. All right. So I am starting the recorder. Okay, it's already started. And I do apologize because the last class meeting was, oh, not that's not for this class. I think that was for the Monday Wednesday class. I was recording the wrong screen, so the audio part is good, but the screen was not capturing the correct part. Anyway, all right. So for this class here, what I'm going to do is to show you guys how to make sure that the extension that you are using for your submission is correct. So the way it is done is you have to go to the file manager. Okay, so file, it's not manager, file explorer. There we go. So if you go to the file explorer, you'll go straight to the option. Okay, or you can go to file explorer and then go to the option. But I think under settings, typically if you type file explorer in the little search box, it will show you file explorer options. So go straight to file explorer options. And then in there, go to the View tab. And under the View tab, under Files and Folders, there is an option of hiding extensions for known file type. So you want to uncheck it, which is this one here. Do you guys see it on the screen? So there's a box that's called Hide Extensions for Known File Types. So if you uncheck it, make sure you apply and then click OK. So now any text file will show up with an extension of .txt, and you will be able to save your file as TTP-ASM. So let me go ahead and actually show you guys how to do that too, because it's actually more complicated than it should be. Thanks to Microsoft's way of thinking about how to make things easier for people. So we'll just say, okay, this is a sample program file. Okay, no big deal over here. So when you go to File Save, okay, you have to choose not to save as type text document. Instead, you choose all files. So this way, it's not going to enforce the .txt at the very end of the file name. So now, if I type test.ttp-asm, it would actually be saved as ttp-asm. So let's double check and see whether that really is saved, with the TTP-ASM as an extension. So if I go to, okay, let me see how I can do this. I think it's usually saved to the documents folder. So if you start up a CMD, or the command line interface, it does not hide extensions from here. So if I do a dir, we can see, okay, I have no idea where I saved the file. Was it on the desktop? Uh, I wasn't paying attention. It was on the desktop. Okay, fine. So we'll go to the desktop, and on the desktop, it's definitely just TTP-ASM without the extra .txt extension. So there are two things you need to do to make sure that you save the file with the extension of .ttp-ASM. The first one is to turn off the hiding of known extensions, and then the second one is when you save the file, make sure you save it with you know turn off save as type text document. Instead, specify all files. So in that case, it will let you use whatever extension you want to use. All right. So is that okay? Does everybody understand what I'm talking about and how to follow these steps? Okay, very good. Alrighty then. So I can leave this part up, although I don't think I have to get back to it anytime soon. So what we'll do today, okay, I left a note in the announcement to remind myself, what to do for today's lecture. So if you go to the announcements and you go to topics for today's date, Then the first thing we're going to do is to use .6 plus to specify the return address, because up to this point, we have always used labels to designate, okay, when the function is done, return to this spot over here. And we always use a label. The problem with using a label for that purpose is you end up with a lot of labels, okay? Because for every function call, there is going to be a label. If you use the wrong label, the assembler doesn't know, okay? You will just end up with the program, returning to the wrong spot, because you're using the wrong label. You push the wrong return address on the stack. So that's why, using the .6 plus approach is a little bit easier. So the first thing I'm going to do is to show you a program using this new method of specifying the return address. So let me put my text window over here, because that's what I'll be using to demonstrate programs for the most part today. All right, so I'm gonna edit a file which is just called return.ttp-asm. So in this program, I just need to call main and then return from main. Okay, that's what I'm going to do. So LDID with 0, it is optional, but it's kind of good to know that we are initializing the stack pointer. And then we have LDIA.6 plus, and I will explain why it works. Okay, so just give me a little bit of time to write the program first. Decrement D, STDA, JMPI to main, and then after main comes back, we just have to halt. And here's main. Main just has the usual return code, which is LDBD, increment D, JMPB. Okay, so these 3 lines are typical that we use for returning from a function back to the caller. All right, so now back to what the dot and why we have .6 plus. The one single dot on line 3 is the address of the opcode of the LDI instruction. Okay, so is that sentence okay? Does everybody understand what I mean by that? The dot is representing the address of the LDI opcode. Are we good? Okay with that? All right, okay. So the LDI instruction takes 2 bytes, okay? In other words, from the dot perspective, dot plus 0 is the LDI opcode itself. Dot plus 1 is the constant that is specified to the right-hand side of the comma, okay? On the next line, this decrement D takes only 1 byte, so this would be at location dot plus 2. And because decrement D only takes 1 byte, the next one is going to be at dot plus 3. But JMPI takes 2 bytes. So that means this is, okay, let me double check. That's plus 1, plus 2. This one takes 2 instructions. So this would be dot plus 5, okay? So that means the halt instruction is going to be dot plus 6. It is exactly 6 bytes away from the opcode of the LDI instruction. And that's why dot 6 plus, which is dot plus 6, but expressed as a postfix notation, works. So yes, go ahead. The dot notation has nothing to do with the stack. It has to do with the address of the opcode of the instruction on that line. So in this case, the dot is the address of the opcode of the LDI instruction on line 3. Yes. Yep. For specifying the address of that line, the first location of whatever line that contains the dot is what the dot is representing. You're looking at it. This is how we can specify the return address without using a label. No, we still have to use labels in many other cases, but when it comes to specifying an address that is always at a certain offset from where you need to calculate the address, we can use this particular approach. All right. So how do you check it? Because I just made a claim that this works blah 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 this way, right? So how do you double check it? Exactly. Okay, very good. So we're going to submit this particular program, and not only is it going to assemble, but it's going to run it too. So we'll go ahead and do a submit of call return.ttp asm. Oh, this is also a good time to remind everybody that getting Reefer Spider to work is going to be really helpful. Okay, so if you need any help with setting it up, I think we might have time today to do that. Okay, we do have a lab today, but it may not take the entire 80 minutes to do that. All right, so this is all done, and now we're switching to the assembler, which needs a refresh. There we go. All right, so this is just the usual run trace, which is not what we really want to see. We want to go to the assemble tab. In other words, what we want to do is to go to the very same instruction or the line that we want to analyze and go like, did it figure out the correct return address? So what we can see here is column W is the address of the first byte of that line. Okay, that's one of the very first things that we introduced when we talk about the TTP ASM tool set is column W in the assemble tab is telling you the address of the first byte on that line. So the 6C is located at exactly 03, the location. Okay, this is the opcode, this is the constant, this is the next instruction, which is the decrement D. This is the next instruction, which is the store instruction. This is the next one, which is the JMP instruction. This is where it's supposed to go back to. This is where the function is supposed to return to. So it did specify the correct location to return to. Is that okay? Yep. No, dot 6 plus evaluates the location of that line and then compute 6 and then they add 6 to that location. So so the location is 03. We're adding 6 to 03, and therefore we end up with 09. Yes. That's because okay, let's go to the assembler manual. There's a reason why I wrote a manual. So in the manual, it is fully explained here. So if anyone wants to get a little bit more of a detailed explanation, a postfix notation may use a dot to refer to the current location, the location of the line where the dot is. So this means the earlier definition of L1, okay, because typically when we want to define the location, it's just L1 and then the colon. It really is the same. It's really a simplified form of L1 colon and then a single dot, because the single dot is representing the location of that particular line. Okay. Six, it's just 6. The value 6 added to the dot, but it has to be, but to the current location, yes. Wherever that dot, whatever line that dot is on, it has a location associated with it. The dot is representing that location, and then you use dot 6 plus as an expression to calculate that location plus 6. Yep. Mm-hmm. How many bytes? So when you yes, so you're basically counting. This is 0, 1, 2, 3, 4, 5, 6. So that's where we need the function to return to. That's why we are counting 6 bytes from where the um, LDIA is located. Because when we looked at the LDI instruction, when we trace the execution cycle for the LDI instruction, we know that the first byte is the opcode itself. That's what we fetch. But the actual, okay, we go to the opcode table. The opcode table actually gives you a clue of that too. So when we go to the opcode table, LDI is documented as the register X is the reference of PC++, because we have to skip the location where the constant is in order to make sure that we don't execute the byte that is used to represent the constant as an opcode in the next fetch cycle. So you can also see that in the assemble view. So in the assemble view, we can see that anything that has an I, like LDI, it takes 2 bytes. JMPI also takes 2 bytes. Mm-hmm. Yep, you're welcome. Yep. One more thing. So you're loading the location of something, adding 6 to it. Okay, so the dot is representing the location of associated with that line, which is 3 in this case. And then 6 plus, dot 6 plus is the postfix way of saying dot plus 6. You basically tell what the value that you need to operate on first, then you operate on the values. Dot plus 6 is an infix notation. We convert that into dot 6 plus as a postfix notation. And if anyone needs help with postfix notation, the manual actually also contains a link to postfix notation. So this part here, note that the label definition can utilize postfix expressions. And here's a link to learn how to do the conversion. And if you want the conversion actually done for you, here's a link to a calculator that can also convert infix to postfix notation. So these are the tools that you can use to kind of learn how to do postfix conversion. All right. So are we doing okay? All right. So try to read the assembler manual, especially this particular section, if you want to learn more about the dot notation and also the postfix notation. All right, so getting back to today's main topic then. So let me go back to the announcement so that I can remember what to do. So I am considering this done for now until I hear additional questions. So now we're going to continue with the program that I finished in the previous lecture, but I never really run it in the previous lecture. So we're going to do that today. So I got the program already in, so we'll go ahead and take a look at both the C and also the assembler implementation. It's called struct.c and struct.ttp-asm. So if you received the file earlier, you can also have it on your own computer. So the nice thing of maybe I forgot to decompress it. Okay, so let's need. Oh, it's in the temp folder. I forgot that it is in the temp folder. There we go. Okay. Does this look familiar? Okay, excellent. So what we need to do is to I'll just go ahead and recap the C code first, and then we'll go to the assembler code on the right-hand side to basically figure out how this is going to run. So one thing that basically what you need to develop right now is to be able to look at the C code and, I guess in your mind, visualize how the stack is going to be used. Okay. So in the assembler, okay, we have the entry code here, and as we have talked about a little bit earlier, I don't need that label anymore. I can use .6 plus over here, and then I don't need that label anymore. Okay, so the program would behave exactly the same way even without that. But the cool thing is everywhere that I need a label, I don't need that label anymore. Now this program only has one single call and one single return, so I don't have any additional places to replace a label with .6 plus. Now remember, the .6 plus only works in this particular sequence of instruction. You can move this instruction to here, but then you're going to have to change .6 plus to .5 plus, because in this case, the halt instruction is now only 5 bytes away from the LDI opcode, because I exchanged I switched the order of the decrement D versus the LDIA instruction. So the first question is, can I actually switch the ordering of those two instructions? So in order to answer that question, you have to basically ask, do these two instructions have dependency? In other words, does one instruction depend on the outcome of the other instruction? And the answer is no, they do not. Okay. Does decrement D make use of register A in any way? Nope. Okay. How about the LDIA blah 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 instruction? Is it possible that it would use register D? Nope. So these two instructions are completely independent, which means they can be executed in any order or even together at the same time. But the processor that I designed is not capable of executing multiple instructions at the same time, so I always have to specify the order. But if you switch the order, the .6 plus becomes a .5 plus, because when you do the counting, the dot is here. This is dot plus 1, 2, 3, 4, 5. Because the decrement D instruction is no longer here. So that's why the number of bytes from where the LDI opcode is to the halt instruction is now 1 byte fewer compared to last time. Okay, go ahead. Every LDI instruction takes 2 bytes. Okay, so that would be 0, 1 from the dot, because the dot is referencing the location of the LDI opcode itself. So 0 and then 1. ST instruction takes only 1 byte, and then the JMPI instruction takes 2 bytes. So that means 0, 1, 2, 3, 4, and then 5. Okay, go ahead. You had a question too?
Yeah, I was saying that you can't, so LEIA with the dot five, you can't just put return address there, like is that not the other, are they the same thing?
Okay, what do you mean by return address? We don't have that label here anymore. Now, if you want to use the label, okay, so are you referencing return address as a label? As a label? You can still do the label.
But you, I'm just trying to confirm that you changed it dot five plus, I mean, return address to dot five plus.
Well, it was .6 plus before I switched the order between line 12 and 13. So this part of the discussion has to do with why I had to change .6 plus to .5 plus when I switched the order of line 12 and line 13. It has to do with whether decrement D is between the LDI instruction and the halt instruction. Because if I change it back like this, then the LDI instruction is between the LDI opcode and the halt opcode. So that's why it needs to be .6 plus, because that byte is in between where I specify the location and where that location really is. Not a whole lot. Okay, the only visualization is how you do the counting. So right now, this is 0, 1, 2, 3, 4, 5, 6. But if you switch the order, then if you do the counting from where the dot is, so now you're counting 0, 1, 2, 3, 4, 5, because decrement D is no longer between where the dot is and where we need to specify. Question? Nope. Okay. All right. So keep that in mind, okay? Because both of these versions are correct, okay? It's just that it's the way that you calculate, that needs to change. All right. So that's somewhat of a minor point for this, you know. But yes.
So is this just a way to like minimize the lines of code by removing the return address?
No, it is a way to eliminate the use of labels. Not so much to reduce the number of lines, but to reduce the possibility that you can use the wrong label. Because if we use a new label for every time we call a function, eventually you end up with a lot of labels, right? So unless you make very explicit name for the label, where it is really clear by looking at the name of a label, this is a return from this to back to there, it is quite easy for people to use the wrong label. And if you use the wrong label, the assembler cannot help you. The assembler can only report a problem when you are referencing a label that does not exist. But if you reference the wrong label, it will simply put in the wrong return address, and then your function will function correctly, but then will return to the wrong spot. And then you'll be scratching your head. It's like, why did I go back to here? Because you specified the wrong return address. But using this method, there's no confusion of using the wrong label. So that's why I personally prefer to do it this way. All right. Okay. So what we want to do is to figure out what is on the stack. The program execution starts here, and the first thing that we push on the stack is the return address of main, getting back to the halt instruction so that we can stop the entire program. So that's where the first byte is. So the way I'm going to do it in today's class, I'll give this method a try today, is to use a picture to demonstrate this, okay? So we'll see how this goes. Okay, so let's say this is memory space. This is location FF, location FE, location FD, location FC, location FB. I think that's all we need for this case. Okay, so this location here is used as a return address, and it is used so that main can return to the entry point. Okay, so location FF is utilized for that purpose. And then we switch back to the code and go like, okay, so what do we do in main? So the two label definitions here do not do anything at all. In other words, label definitions by themselves do not do a single thing when your program runs. Okay, all they're doing is kind of like a symbolic name. Okay, basically we are saying, oh, every time you see main underscore ABC, it's the same as looking at 0 itself. Every time you look at main underscore LVS, it is the same as, oh, let's do some calculations here. It is 0 plus x underscore size, which turns out to be 3 in this case. Okay, so main underscore LVS is the same as the integer 3. So that's what labels are. They're really just symbolic names for some kind of numerical value. Is that okay? Okay. So they don't do a single thing, but these two instructions do something, right? Because what this is doing is loading basically 3 into register A, and then it subtract 3 from register D. So that means register D, which is our stack pointer, is going to point to 3 locations lower. So that means, from the perspective of the picture, after we push the return address, this is where the stack pointer is going to be. However, after we subtract 3 from the stack pointer, this is going to go like, oh, okay, we are supposed to go 3 bytes lower. So this is where the stack pointer used to be, and this is now where the stack pointer points to. So that's the end result by the time we get to the line 22. When line 22 is done, the stack pointer will be pointing to location FC. So the question now is, so what are these 3 bytes for? Well, these 3 bytes is the local variable of main. So let's take a look at the C code and the assembly code. If you look at the C code, we have one single local variable called ABC. But what is the type of the local variable ABC? It's a struct X, right? Particularly, it is a struct X, and struct X is defined up here in the C code. And if you just look at the structure definition, how many bytes do you think struct X is going to take? 3 bytes, exactly 3 bytes. Okay, so basically, these two instructions is allocating for my only local variable, which is ABC. So from the picture perspective, this is ABC dot M1 member 1. This is ABC dot M member 2. This is ABC dot member 3. Is that okay? Because this is a very important picture because it shows you graphically, what is on the stack at this point. Are there any questions? Yes.
Okay. Member 0, 1, and 2. So is that just representing that there are 3?
Oh, 0, 1, and 2. Okay, you're correct. Okay. You're correct. So let me fix that. Let's see, where's my eraser? There we go. I think that's my eraser. So let me fix that first. Get rid of this, and then go back and write. This is supposed to be 0, 1, and 2. Thank you. But same idea. Are we doing okay so far? But this also shows you what x underscore m0 is about. This is where ABC is, okay? The address of the structure ABC as a local variable is location FC. That's the first byte of variable ABC. But it is also the location of the first member of ABC as a structure. Is that okay? So that's why the offset of the first member of a structure from the beginning of the structure itself is always 0. Yes?
So stack has a return address, right? And then the structure ABC is just filling those three spaces, right?
We are not filling any spaces. It is how those 3 spaces are allocated for. So right now, we haven't done anything with these 3 bytes other than having the stack pointer to point to here.
So we can actually move the stack pointer, it just automatically does that when we like initially.
What? Okay. What do you think this instruction does? Okay, line 12.
Moves the stack pointer down one, right?
Exactly. And what do you think these two instructions do? Lines 21 and 22.
Loads the label.
And what is that label? What do you think is the value of main LVS? I mean, anybody can answer the question. 3, that's right. Okay, main LVS is 3. So we are putting 3 into register A, and then subtracting DA is subtracting 3, which is in register A, from the stack pointer.
How did you get 3 from main LVS?
Because of how these things are defined.
Oh,
That's what we talked about on last Thursday. So that's why it is.
main underscore LVS. Where is it like you define to where it has anything to do with those on the top? Like how do you relate that to those the M0, XM1, XM2? Because it doesn't have the same name. So it's like how do you know that main underscore LVS is 3?
I'm not sure I understand the question.
Kind of like point for
Yeah.
so what I'm saying is
Yeah.
Is there any like declaration up here that relates this to
No,
mean
it's
3?
right here. Main LVS is defined on the line before, right before.
Okay, that makes sense.
But this is the program that we talked about on last Thursday. So I was expecting people to kind of study about this a little bit before today. So it's kind of important to kind of have that background knowledge from the previous lecture. So are we good? Okay. All right. So we are now on line 22. We're done with line 22. So that means we have register D pointing to location FC at this point. Then what do we do? Well, in the C code, the only thing we want to do in the C code is to say, let's change the second member, which is M1 of ABC to a 0, okay, which is already a 0 to begin with, but we want to kind of make sure that we put a 0 there, okay? So the way it is done is we have to first find the location of ABC first. So main ABC is basically just 0. So that means this register A is a 0. And then we add the stack pointer to 0, which means we register A just becomes the stack pointer. So in the picture, it means now we have register A pointing to exactly the same location. And then after that, we go like, okay, but I don't want to change the first byte of the structure to a 0. I want to change the second member of the structure to a 0. So now the question is, I know where the structure is. Where do I find the second member? So the second member is defined, or the offset to the second member is defined up here. X underscore M1 is defined to be X underscore M0 plus 1. But M0, X underscore M0 is a 0. So that means X underscore M1 is just 1. Okay, it is just 1. But that 1 is representing the number of bytes between the second member of the whole structure and the very beginning of the entire structure. Okay, so that means, oh, okay, this is where I can find the second member called M1, but the structure itself is located here. So how do we do that calculation? So the way we do that calculation is we load the offset to the member that we need to access into a register, and then we add that register to the address of the structure itself, which is already in register A. So after this is all done, register A is now going to point here. Okay, so I will call this 3, I will call this 4, so that things are kind of sequenced. So when register A is pointing, it has the value of FD, it is pointing to, it becomes the address of member M1 of the local variable ABC. Is that part okay? All right. So when we get back to the C code, then we go like, oh, okay, so we now know where we're supposed to store the 0. So now we put a 0 into register B and then copy register B to where register A is pointing to. So that means, we finally put a 0 over here. So that's, this is step, I don't need a ruler. Go away. There we go. So that means, we are now finally putting a 0 here. I'll call this, step 5. That doesn't work, does it? Okay. We'll call this step 5. There we go. Make a call out. Is that okay? So the program is now done. Okay. This is the only statement in the C code that does something useful. And then we return a 0. Well, there's no need to actually return a 0 because nobody cares about the return value of main. So that's why, I don't bother to return anything. But we still have to deallocate the local variables of main. So line 31 and 32 together is deallocating the local variable space. In other words, the stack pointer, okay, register D, used to be pointing here, and now it is pointing back here. So that's step number, I'll call this step number 6, because we are deallocating the space that was earlier utilized by the local variable. The local variable is of no use at this point because we're at the end of the main function. And then after that, we have the usual return code, which is basically going just pop the return address into register B. So whatever is in the return address, this goes into register B. I'll call this step 7. And then the stack pointer points all the way back up to location 0. I'll call that step number 8. And then the program continues to, with whatever register B is pointing to, which is the return address, which is also the address of the halt instruction, and the whole thing is done. Okay? So this sounds great in theory, right? Does it actually work this way? How do we know whether it works this way or not? So what do you do to kind of check whether this is working just the way that TAC describes it? And you go to the assembler, and you go to analysis. So what I just described in words and a picture, excuse me, is actually reflected here. But this is not the program because I haven't run that program yet. Don't think. So let me go back here. Make sure we save the file first. :w, there we go. And then go ahead and run it. Okay, so we'll change this one to the river spider folder and then run struct.ttp-asm. Excuse me. Now it is run. So this is the whole trace, okay? This is where we push the return address. This is where we allocated the 3 bytes for the local variable ABC. And if you scroll down a little bit, this is where we store a 0 to member M1 of ABC. And this is where we deallocate those 3 bytes that were used earlier by the local variable. This is where we pop the return address into register B. And this is where we increment the stack pointer as a part of the pop operation. And then we end up with the halt instruction. In other words, the trace is describing exactly the same thing that I just described in words. Okay, and that's why it is important to get River Spider up and running, because you can still do something like this without River Spider, but the process is painfully complicated. Okay, there are just a lot of steps in between. So doing this is super important if you want to debug the program that you're going to be writing from this point on. All right, so I'm just going to pause to see if there are any questions I can answer, and then we'll proceed. Yes?
So in C code, struct ABC saves, but in on the right side, we are deallocating local variables. So ABC is disappearing. We are deleting it, but on C, it's staying.
Nope, it is gone too. In other words, when after main has returned, the storage that was initially used by ABC is gone as well. All right, so how do we know that? Okay, because TAC just made a claim. Okay, so every time I make a claim, you want to think about, but how do I make sure that what TAC is saying is true? Okay, so I'm going to write a program to show you guys what you can do to verify that. Okay, now do I expect you guys to be able to come up with sample programs like this or the idea to do it like this? No, not exactly. Okay, but that's why I'm here. Okay, that's why they pay me the big bucks, which is about the same as the early career median salary of someone who's going into the industry of computer science. I started working in 1990, so that's what, 34 years ago. And when you guys get your bachelor's degree, go into industry and work maybe a year or two, you'll be making the same money that I'm making now. That's a good thing, but that's a catch. What is the catch? There's a conditional to this whole thing. Only if you land a job. Okay, just because you have a bachelor's degree in computer science is no guarantee whatsoever that you can land a job. So I just want to point that out, okay? I don't want to disappoint or discourage anyone in this class, but we need to be realistic. Okay. All right. So after that depressing news, let's go ahead and focus on this program. Okay. So we'll just go reuse. Okay. I'll call this reuse. Okay. So I'm gonna write two functions. Okay. They can be super stupid void functions, and this one I was just go like, okay, let's do some structures too. So we'll say struct eggs, same as before. Um, this time I'm just going to use integer because the whole point is not to translate that into assembly code anymore. So I'm just have a bunch of members in this structure. So all this is going to do is to say struct eggs. I will use variable name v1, and then we say v1 dot c is 27, okay, or 28, doesn't matter, doesn't really matter. And then I have void g, kind of the same thing. You struct eggs v2, v2 dot c. This time is getting the value of -4. Okay, and now we have main, int main, which is going to call those two functions, f and g, and then return 0. So this is apparently a pretty stupid program, okay? But there's a point to this entire thing, okay? So we'll go ahead and run this program in GDB to illustrate that point. gcc-g-o reuse.c, gdb reuse. Okay, there we go. All right, so we're going to put the breakpoint on the two functions, function g and function f, okay? So you can do it like this in GDB. In other words, if you say b, which stands for breakpoint, and then the name of the function, it automatically put the breakpoint at the entry point of the function, which is kind of handy. Okay, so now we run the program. So this is the first line it stops, which is the first and only statement in function f. The only thing I really care about is where is v1, okay? So v1 is at a location that is blah, 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 64. Is that okay? All right. So now we continue the execution of the program. And now it stops in function g because I called f first and then I called g. So now we want to ask, where is v2? What do you think v2 is at? I call f first. F has some stupid thing to do with the structure that is a local variable, and then it returns. And then I call g, which has its own local variable, and they're exactly the same size. So what do you think is the address of v2? You got a few choices. It's above where v1 used to be. It is at exactly where v1 used to be, or it is below where v1 used to be. Okay. What do you mean by 59? 59? Okay. So has everybody placed your bet? My bet is on the second option. It is at exactly the same location. Why do you think that is the case? Because function g deallocated the storage that it was using for its own local variable when it returned. So when function g is called, it is reusing exactly the same space as what function f was using earlier. Okay? So you go like, I don't believe that. Okay, that is nonsense. So what you can do is to say, well, okay, this program is not going to illustrate it. Okay, so I am going to change the program just a little bit to illustrate a really obscure point. In other words, I'm only using member B in this case, and this one is using member C, so leaving member B uninitialized in quotes, okay? So we're gonna compile the program again, GDB again, put a breakpoint on F, put a breakpoint on G, run the program, continue. So we are now back to exactly the same place as we used to be. So the question is, we are now in function G, who never initialized member B of its own local variable v2, right? if I were to say print v2.b, what do you think I should see? Okay, I give you three choices. Okay, four choices. First choice is, GDB says it's uninitialized. I don't know what the value is. Okay, that's one. Two is it would display some integer, except it's just some mumbo jumbo that has nothing to do with anything in this program. It would be zero, okay, because the idea is every time we allocate local variables, it is all zeroed out first. Or four, it is 28. What do you think? Yep, it is 28 because the invocation of function g reused exactly the same space as the invocation of function f. The leftover, even though we are not supposed to see it, we are not supposed to rely on it, it is still on the stack. That 28 that we put into member B of V1 when we were calling f is still on the stack. So by the time we call function g, it says, oh, I'm just going to allocate these bytes for my own local variable. Well, it's the same space as the local variable of function f. So is this helping to illustrate the point that I was trying to say earlier? Because you're allocating and then you're deallocating, you're allocating and then you're deallocating. So the stack space is constantly being reused. Every time you call, it's allocating some more, but every time you return, it is deallocating the amount of space that particular invocation was using. So this is an important point. Okay, if there are any particular value to this class, this is one of those. Okay, if you do not initialize your local variables in C and C++, they simply pick up whatever is left over on the stack at the time when the function says, oh, I'm going to need this space for my local variables. So there are no particular value in local variables when you declare them. So you kind of have to keep that in mind, because very few other programming languages is like this. Okay, in Python, in JavaScript, there's always something. Okay, every local variable is quote unquote initialized. Now in JavaScript, it is initialized to a value of undefined. But guess what? Undefined is an oxymoron because undefined is actually a defined value. It is consistent. Okay, but in C and C++, there's no such luxury. Okay, it simply says, this is the space for this variable. What is the value of this variable? Whatever is left over from the last time somebody used this space. That's it. Is that okay? All right? All right. Which also means, hackers can potentially exploit this fact of C programs. If a hacker can find out how a program has okay, maybe I shouldn't go there, but basically if a program already has a programming flaw of letting um, a portion of the memory that is not supposed to be seen, being reported to whoever is using the program, then this can potentially be a problem because whatever was using that space before can leave behind some really important information like encryption keys and whatnot. Okay, so there's a program called there's a exploit called hard bleed. So anyone who is interested in this sort of thing can look up hard bleed and just go over the first few two paragraphs or so. That is basically what happens when programs are not written in the correct way and someone else figures out, oh, okay, I can craft a request to this server so that it would actually reveal the content of memory location that I'm not supposed to have access to. So this is kind of interesting, okay, from the perspective of assembly language programming in C and C++, and also cybersecurity. It kind of overlaps in all three circles. All right. So do we have any questions about the program that we were looking at earlier? In other words, let me go back to the program that we were looking at, this one. So we are all good with this one? Okay, all right. So if I did not write any notes down, okay, I would have forgotten what I'm supposed to talk about next. So this is just my way of telling you guys it is super important to write notes because our short-term memory is actually very short-term, okay? So, but because I took note, okay, I can now read this and go like, oh, right, I'm supposed to demonstrate the implementation of this particular program, okay? The reason why this program is important is, I'll just put it this way, it is related to what you need to do for your next homework assignment. Okay, so you're going to have overlapping programming to do. So the program that is due on Thursday, hopefully you're close to being done with that one. But this is a new programming assignment that is due also in a week. So we now have overlapping programming assignments to do. So we'll take a look at this program and ask, how do we implement this? Okay, so we'll go back to the command line and how should I call this? 12. Okay, we'll just call this 12.c TWELVE. I think I spelled it correctly. There we go. And then we'll do the same thing. You'll display both the C code. The C code is going to be on the left-hand side, and then the assembly code will be on the right-hand side. TWELVE.TTP ASM. Okay. So let's go ahead and look at the C code. Now, I know I specifically made it kind of difficult to read because I was too busy to do this, and I just decided, oh, we'll just use the fewer lines of code to do this. So Johnny is a function that returns 5, and Ryan is a function that returns 7. 12 is a function that returns the sum of what Johnny returns and what Ryan returns. So one returns a 5, the other one returns a 7. 7 plus 5 is 12. So then we have main, which has a local variable x, which is going to store the return value of 12, which is exactly the numerical value of 12, and it's done. Is that okay? All right. So this is the kind of neat thing about C, is you can write the program like this. You can even do it like this. And the C compiler says, I still know what I'm supposed to do. But the human look at this and go like, what is that? All right, so we'll do it in assembly code now. So no op, and the first thing we need to do is to call main, or initialize the stack pointer first, and then we call main. LDI A.6 plus, decrement D, STDA, that pushes the return address, JMPI to main, and then when main comes back, we're going to stop the entire program. So typical entry code, when we treat main as a function. So now we go to main. Main has one local variable, which is x. So now we say main x is 0. Main LVS, or local variable size, is main x 1 plus, because x only takes up 1 byte. And now we actually write the code, LDI B with main LVS, subtract that much from the stack pointer to allocate for the local variable. And then what I usually do is I just put in the code to deallocate right away, and then I return to the caller, LDBD, increment D, JMPB. So this stuff here is, I would say at this point, this stuff is somewhat boilerplate, okay, because every function has kind of these elements. All right, so now we are going to pretend that 12 is already implemented, and we are just going to call 12, okay? Now 12 does not have any arguments, okay? There's no argument to push, so I can push the return address right away. So LDIA.6 plus, decrement D, STDA, that pushes the return address, and then we have a JMPI to 12, And when it comes back, I don't have any arguments to undo, so I don't need to increment D, for that purpose. The return value is supposed to be in register A, so I can now store register A to local variable X. So, but first I have to compute the address of local variable X. So the pattern to do that is LDIB main X, which is the offset of the local variable X from where the stack pointer points to. And then we do an add BD. So now B has the address of local variable X. Yes? It's defined up here. The offset is the number of bytes between where the stack pointer points to and the thing that you want to access. That's the offset. I just call it the offset. Say again? It is the number of bytes between where the stack pointer points to and what that thing is. In this case, that thing is local variable X. So where the stack pointer points to and where local variable X is. That's the offset. All right, so, right, okay. So we now have the address of X in register B. So STBA is going to finish the assignment operation, which is here. All right, so now it's time to implement Johnny, 12, and Ryan. Okay, so I can put one more line feed over here. There we go. Okay, so these function names have to do with certain characters and last name of actors and actresses. All right, so let's implement Johnny first. So Johnny is a reference to Johnny 5 in the movie Short Circuit. Okay, so if you don't know the reference, it's okay, but I do want to kind of get you guys to know, why did you name this Johnny? Because Johnny 5 is alive. LDBD, increment D, JMPB. Okay, same three instructions. Every time we need to return from a callee, a function, to the caller, it's the same three instructions. Okay. Ryan is named after Jerry Ryan, who is the actress of 7 of 9 in Star Trek Voyager. So it's the reference. Okay, you guys don't really have to know that, but okay, there we go. So now the big question is, how do we implement 12, TWELVE? And some people would say, oh, you just have to do a LDI A12 and then everything else being the same. Yes, I could have done that, but then I would not be illustrating what the technique that you need to know for the program that you'll be writing, for the assignment that I'm assigning today. All right, so let's take a look at 12. We need to compute the sum of the return value of Johnny and the return value of Ryan. Go like, okay, doesn't sound too hard, right? We know how to call Johnny, so let's call Johnny first. So let's specify the return address. You can see how this is handy now. I don't need to define a new label for every single time I need to call a function. So decrement D, stda, that pushes the return address, and this will continue execution at Johnny. And by the time I get back to this cursor location, I would have register A containing the return value of Johnny. Okay, which is good. Okay, so you go like, okay, I'm guessing we also need to call Ryan. Okay, so let's go ahead and call Ryan. LDI, I cannot touch register A because register A has the return value of Johnny, right? So I'm going to use register B. Okay, well, which is fine. You can do that. Decrement D, stdb, jmpi to Ryan. Well, we have a problem now because register A currently has the return value of Johnny. Guess what Ryan's going to do? Overwrite register A. You go like, okay, can we do this? Can we just copy it to another register? Okay, can we just do a CPR CA and then later on use register C? The answer is yes and no. Okay, isn't that confusing? Sounds like Schrodinger's cat kind of problem. No, it is not. This one is actually very definite. What is the agreement between the caller and the callee? Can someone pull that contract out and tell me, can I rely on a callee, a function, to preserve the values of registers A, B, and C? The answer is no. Okay, so even though in this particular case, Ryan does not mess up register C, I cannot rely on that. In other words, I always have to make the assumption that a callee, a function, is going to mess up all registers A, B, and C. So that means I cannot just copy it to another register. So what do you think is a safe place for me to say, I'm going to stash this over here because I need it back later? On the stack, exactly. Okay, so the stack is useful in many, many ways. Okay, and this is one of those. It's like, oh, I just need to stash this, I need to save it for later. So you can now push it on the stack. Okay, so that means, instead of doing a CPR, I'm going to push it on the stack. So to push register A on the stack is really just decrement D, STDA. So this push the return value of Johnny. Is that okay? So nobody's going to touch it now, okay? Because it is safe on the stack. I'm not counting on it being in a register anymore. So by the time I get back from Ryan, which is at this point here, what do I have? Register A has the return value of Ryan, okay? Because that's part of the agreement, okay? If you have anything that is a scalar to return, it's going to be returned through register A. But then what about the return value that I need, like the return value of Johnny? Oh, it's on the stack. So what I can do now is I can pop it from the stack. So now I can do LD, BD, increment D. So these two instructions together is popping the top of the stack into register B. So register B is now the return value of calling Johnny. So now I have both of those. I just need to add instruction, add A, B, and now register A becomes the sum of calling Johnny and the return value of Ryan. I'm just going to pause here, okay, and see if you guys have any questions. Yes?
Doesn't this mess up offsets?
Yes, it does. Yep. Yep. If you had any local variable or parameters, everybody is now 1 byte off from where they're supposed to be. Because remember, the offset is denoting how many bytes is this thing from where the stack pointer points to, but that reference point is after all the local variables are just allocated. I just put one extra thing on the stack. So that means the actual offset to all those items, they are now 1 byte more than before. Okay? So that's a very good observation, okay? Because that observation, the rest of the class should thank, what's your name? Mohammed, for making that observation, because which also means you might want to write it down. Because in order to implement the program that will be assigned today, this becomes important, okay? So you might want to write down what Mohammed just said, or make note of the time right now, which is about 10:10. Okay, so you might want to write it down because you might need to revisit this. Okay. All right. Now this is not the first time you see this either. Okay, this is actually the second time you see a technique like this. The first time you see this is when we were doing the lab and there was a function called literally 5, F-I-V-E, and returns a value of 5. But then there's one case where I'm adding the return value of 5 and the return value of 5, and that technique, the technique of saving and restoring, the return value, was already utilized in that particular program. I can point out which program later on, but right now I want to test this program. Okay, I want to see whether this works the way it's supposed to. So let's go ahead and test it. What was it again? Called 12. Yep, TWLV, like that. All right, so we go back to the trace, and it's kind of long, okay? So I'm just gonna shortcut it a little bit and see whether 12 is stored to local variable x, and it did. Is the stack pointer balanced? Yes, it is. Are we ending up at the halt instruction? Yes. So the program basically worked as expected. Is that okay? Now, how do we study at this point, for this class? I'm not giving you guys any more reading modules, okay? Because everything that you need to know is already introduced. The question is, how do you apply what you have learned? How do you apply the knowledge to actually write the code to implement C programs? Okay, so that really is what we are doing from here all the way to the end of the semester. Okay, so each class, I'll be going over some sample programs. I'll be illustrating, this is the C code, this is the assembly code, this is the C code, this is the assembly code. But the actual knowledge that you need to apply to write all those programs have already been introduced. In other words, I'll be reusing the same stuff that we have already talked about over and over again, just in different context. Is that okay? All right. One of the tools that you can use for studying purposes is this tool over here. Okay, it doesn't look like much. Okay, it looks kind of cryptic, but every time you see the stack pointer changing, every time you see D equals to something, you have to ask, what is happening to the stack? Because I can see the stack pointer just changed. Every time you see a memory location being changed, you have to ask, what did I just store? Okay, if that location turns out to be where the stack pointer points to or above, then you'll be asking, what on the stack did I just change? Okay, so all of those are questions that you need to ask when you're looking in a trace like this. Now, if you put in a lot of comments, which I think you should do, okay, even to the programs that I have written in the class, okay, I intentionally did not write any comments in this code here. Why? Well, it's not to save time, okay? It wouldn't take me much time to type the comment because I want you to write the comment in this code. I will give you all of the code that I wrote in class. So your job when you're studying is to comment it. Now, if you want extra challenge, then you can go ahead and basically ignore my implementation. Okay, you look at the C code and go like, okay, I will try to implement this myself first. Okay, now if you're absolutely stuck, you go like, I don't know what to do, my program just simply won't work. Then you can go back to my implementation and then you document every single line of the code because you need to know why is this line here? What is it doing? Is that okay? All right. So that's really kind of the studying material at this point. Now, depending on what questions you're asking in class, I can give you different sample programs. Okay, so if there's a specific question of, oh, so how do we access a member of a structure that is pointed to by a pointer? Okay, which by the way, we'll be doing a lot later on in this class. Then we'll be writing some code. I'll be writing some code to illustrate how that is done. Okay, so when you're studying and you're going through all this exercise and you come up with a question, okay, you go like, well, well, I understand how this program is supposed to work. I understand that and so on. But what about this one? Okay. So if you have any questions like that, then you go like, okay, I know it can be done, but I'm just not sure how it is done. Send it to me. Okay. We can turn it into a sample program that I introduce during the lecture. So it's kind of flexible right now, okay, the way I introduce your content, but for the most part, it is time for you guys to kind of implement the program, because when you're implementing the program, that is how you're studying, because that's how you make all the connections in your head. When you're in a lecture, sometimes, not sometimes, but most of the time, for many people, they can follow the lecture just fine. It's like, I follow the lecture, I understand what you're talking about, and then you're faced with your own programming task. You go like, where do I get started? Do you know why that happens? I know this is not a psychology class, and I'm not a psychologist, but I think what this has to do is when you're listening to someone explaining something, you only need enough short-term memory to kind of keep track of the context to understand something. But when it's time for you to apply what you have understood to solve a problem, is a whole different process. Okay? So when you use something to solve a problem, that is when it becomes incorporated into your mind. Okay? It will be difficult for you to undo, to forget what you have learned once you figure out how to solve a problem. Okay? So that's kind of what we are doing at this point, is you basically will constantly have programming assignments to do. And in the process of writing those programs, you'll be hopefully making the connections between all the concepts and be able to apply those concepts. All right, so we got about 3 more minutes in today's lecture. How many people are done with the swap function? Okay, we got a few hands, okay. And I'm hoping the rest of the class have at least gotten started with it and have River Spider already up and running, because that's the tool to use to debug the program. Is first you have to think about what do I need to do, and then you think about how do I get it done. Alrighty. Any questions? All right. So for this class, I have office hour right after the lab. So starting at noon, I do have office hour. So if you are kind of stuck with certain concepts, or you want some clarification of the concepts, do not hesitate to come visit me. The lab time is fine too. Okay, so typically the lab has something to do with the concept that I've just introduced. So you can also ask questions during the lab. But I cannot just answer one person's question the entire time, because there might be other people who want to ask questions too. All right, so with this all done, I am going to give you the access code of today's lab. So today's lab is recursive calls. Okay, that's the name of today's lab. And the access code is holodeck. Because in one particular episode of Star Trek The Next Generation, the character Moriarty, which is a holodeck character, tricked Lieutenant Data and Geordi by creating a holodeck inside of the holodeck, so that Data and Geordi thought that they were outside the holodeck, but in fact, when they walked through the door, they entered a holodeck within a holodeck. So that's kind of recursion. So that's why I use the access code of holodeck.
I think I actually remember that episode too.
Yep. I think that's the first time Moriarty was introduced as a character in The Next Generation.
Yeah, I think so.
Yep. All right, so I will step out for a moment. I think you can get started by 10:20, which
One more minute.
yep, it is 10:20 now. Go ahead and get started. All right, so I will be back in a few minutes. And I can stop the recorder.